In 126 AD, Roman engineers completed a building whose roof has not been repaired in 1900 years. The Pantheon in Rome, dedicated to all the gods, converted to a Christian church in 609 AD, still standing, still intact, still receiving visitors every day of the week, has a concrete dome spanning 43.3 meters across its widest point that remains, to this day, the largest unreinforced concrete dome on Earth. Unreinforced. No steel rebar, no internal skeleton of metal, no modern additives or chemical accelerants. Concrete, poured by Roman engineers using a formula they developed, refined over centuries, and deployed across an empire that built everything from harbor walls to aqueducts to the foundations of cities that are still occupied today. And then lost. Not destroyed in a fire, not deliberately suppressed by a religious authority, not stolen, smuggled out in a bamboo staff, or encoded in a secret patent. Simply lost. The Roman concrete formula, the specific combination of volcanic ash, seawater, and lime, that produced a material so chemically stable that it has been gaining strength for 1900 years, while the steel-reinforced concrete of the 20th century is already showing structural decay, vanished from human knowledge with the collapse of the Western Roman Empire in 476 AD. And for the next 1,000 years, while the Pantheon's dome continued to stand above Rome undamaged, while Roman harbor walls continued to harden in the seawater that modern researchers have only recently understood was essential to their strength, the civilization that had inherited Rome's ruins did not know how to make the material that built them. They looked at the Pantheon and assumed it was magic. They were not entirely wrong. But before this story is over, you will understand why one of the most practically consequential materials in the history of human construction was lost for a millennium, rediscovered by accident, industrialized in a way that produced an entirely different and significantly inferior product, and why the scientists who finally unlocked the chemistry of Roman concrete in 2017 discovered something that the Romans themselves almost certainly did not know. Their concrete was still getting stronger. To understand what Roman concrete was, you first have to understand what concrete is. And what concrete is, in its essential form, is deceptively simple. Concrete is a mixture of aggregate, sand, gravel, crushed stone, bound together by a paste that hardens through a chemical reaction into a solid mass. The paste is produced by combining a cementitious material with water. The cementitious material, the substance that undergoes the hardening reaction, is the variable that determines everything about the resulting concrete's properties. Change the cementitious material, and you change the concrete's strength, its durability, its resistance to water and salt and temperature, its setting time, its workability, and its behavior over decades and centuries of structural loading. The Romans understood this empirically, not through chemistry, which they did not practice in any modern sense, but through the accumulated observation of what worked and what did not, applied systematically across centuries of construction, at a scale that provided more empirical data on concrete behavior than any modern research program could replicate. What they discovered, by working with the materials their specific geography made available, was that volcanic ash, specifically the pozzolanic ash deposited by the volcanoes of the Campi Flegrei region near Naples, named after the town of Pozzuoli, where the deposits were most accessible, produced, when combined with lime and seawater, a concrete whose properties were qualitatively different from anything that could be produced with ordinary sand and lime. They called it opus caementitium. They did not know why it worked. They knew that it worked. The Roman construction program that opus caementitium enabled was not merely impressive by ancient standards. It is impressive by any standards. The Romans used concrete to build things that, in the absence of concrete, could not have been built, not because the Romans were uniquely ingenious, but because concrete is the enabling material for a specific category of construction that no other technology available in the ancient world could produce. Large spans, internal spaces uninterrupted by columns, curved surfaces, arches, vaults, domes, that distribute load through compression in a way that stone blocks and wooden beams cannot achieve at equivalent scale. The Pantheon's dome, the baths of Caracalla, whose vaulted halls were the largest interior spaces in the ancient world, the Pont du Gard aqueduct in southern France, still standing after 2,000 years. The harbor at Caesarea Maritima, built by Herod the Great using Roman concrete poured directly into seawater, a technique that modern researchers studying the harbor's remains have found produced concrete that is now denser and stronger than it was when it was first poured. Stronger. After 2,000 years in seawater, the specific chemical mechanism that produces this result was not understood until 2017, when a team of researchers, led by Marie Jackson at the University of California, Berkeley, published an analysis of Roman marine concrete that identified the reaction responsible. The pozzolanic ash in Roman concrete, when exposed to seawater over decades, undergoes a secondary mineral crystallization process. The seawater infiltrates the concrete's pore structure and reacts with the aluminium-rich pozzolanic ash to produce crystals of a mineral called aluminous tobermorite within the concrete matrix. Aluminous tobermorite is rare. It is extremely hard, and its crystals, growing within the concrete's microstructure over decades and centuries, progressively fill the pore spaces and crack interfaces that would, in ordinary concrete, become the pathways through which structural deterioration proceeds. The Roman concrete was not merely stable. It was self-reinforcing. The longer it sat in seawater, the stronger it became. This is not a property that Roman engineers designed into their concrete. They could not have. The chemistry that explains it was not understood for 1,900 years after the Pantheon was completed. They stumbled into it by using the locally available volcanic ash, by using seawater in maritime construction, and by building things on a scale and with a permanence of intention that allowed the slow chemistry to do its work across timescales longer than human careers. They built for centuries. The concrete rewarded them by lasting millennia. The loss of Roman concrete knowledge was not dramatic. It was gradual, structural, and, in retrospect, entirely predictable given the conditions under which the knowledge existed. Roman concrete expertise was not codified in a single text. It was not held in a single institution or by a single class of practitioners. It was distributed across a professional class of Roman engineers and builders, the architecti, the liberators, the mensors, who learned their trade through apprenticeship, through practice, through the accumulated experience of working on large construction projects under the supervision of more experienced practitioners. This is the same knowledge transmission mechanism that produced the barber surgeon's speed, the Jingdezhen ceramic worker's skill, the Amazonian rubber tapper's circuit knowledge, practical knowledge transmitted through practice, not through text. When the political and economic structure that sustained the practice collapsed, the knowledge collapsed with it. The Western Roman Empire's decline across the 4th and 5th centuries was not merely a political crisis. It was a construction crisis. The large-scale building programs that had sustained the professional class of Roman engineers, the aqueducts, the roads, the public baths, the harbor works, wound down as the empire's fiscal capacity contracted. The engineers who knew how to build in Roman concrete stopped building in Roman concrete because there was nothing to build. A generation that does not practice a skill does not transmit it. The children of Roman engineers in the 5th century did not learn opus caementicium because their parents were not practicing it. By 500 AD, the specific knowledge of pozzolanic concrete, the ash, the lime, the seawater, the mixing ratios, the curing process, had left the active knowledge base of European construction practice. It had not been forgotten in the dramatic sense of a fire destroying a library. It had simply not been taught to anyone who needed to use it. The 1,000 years that followed the loss of Roman concrete are not, in the history of construction, a period of stagnation. Medieval builders developed extraordinary skills in stone masonry. The Gothic cathedral, with its pointed arches, flying buttresses, and soaring vertical spaces, is an architectural achievement that Roman concrete could not have produced in the same form. The engineering intelligence of the medieval period was not inferior to Rome's. It was simply working with different materials and different constraints. Stone, timber, mortar, but lime mortar, a mixture of lime and sand that sets through carbonation rather than hydraulic reaction, that is weaker than Roman concrete, more permeable, and dependent on careful stonework to achieve structural integrity. Medieval builders knew that the Romans had built with a superior material. The evidence was around them, the aqueducts still standing, the harbor walls still intact, The Pantheon still roofed. They could examine the Roman concrete directly. They could sample it, test it, analyze it with the tools available to medieval investigation. They could not replicate it, because the key ingredient, the pozzolanic volcanic ash, was not identified as the key ingredient. Medieval investigators examining Roman concrete saw aggregate, saw lime, saw what appeared to be a particularly well-mixed mortar. They did not see the ash as the active ingredient. They saw it as a local variation in the aggregate. The thing that made Roman concrete Roman was invisible to the investigators who most needed to understand it. It remained invisible for 1,000 years. The rediscovery of hydraulic cement, the class of materials that includes pozzolanic ash and its functional equivalents, happened not in Italy, not through examination of Roman remains, but in England. And it happened, as so many things in this series happened, by accident. John Smeaton was a British civil engineer commissioned in 1756 to rebuild the Eddystone Lighthouse off the coast of Plymouth, a structure that required concrete capable of setting and hardening in seawater, a requirement that existing lime mortars could not meet. Smeaton tested every available lime and mortar he could obtain, mixing them with water and measuring their hardness after setting. He discovered that limes made from limestone containing significant clay impurities set harder and more durably than pure limes, and that they set under water, which pure limes did not. He did not know why. He had rediscovered, empirically and independently, the hydraulic property that Roman engineers had exploited through pozzolanic ash. He used his discovery to build the Eddystone Lighthouse, which stood for 123 years before being replaced not because the concrete had failed, but because the rock it stood on had begun to erode. The concrete outlasted the foundation. Smeaton published his findings in 1791. They were noted. They were not immediately acted upon. The next step came from a canal builder named James Parker, who in 1796 discovered that certain nodules of clayey limestone found on the Isle of Sheppey in the Thames estuary could be burned and ground into a powder that produced, when mixed with water, a cement that set rapidly and hardened to a remarkable strength, underwater or in air. He patented it as Roman cement. It was not Roman cement. It bore no chemical relationship to Roman pozzolanic concrete, but it was hydraulic, it was strong, and its name was a commercial acknowledgement that Roman concrete was the benchmark against which any new cementitious material was measured. Even 1,000 years after the formula was lost, Rome was still setting the standard. The invention that defined modern concrete was made in 1824 by a bricklayer named Joseph Aspdin in Leeds, England. Aspdin burned a mixture of limestone and clay in his kitchen stove, the domestic scale of the experiment reflecting both the simplicity of the process and the modest circumstances of its inventor, ground the result to a powder, and found that it produced, when mixed with water, a cement that hardened to a smooth gray finish that resembled the Portland stone used in London's finest buildings. He called it Portland cement. He patented it. And Portland cement, refined, industrialized, and produced at global scale over the subsequent 2 centuries, became the cementitious material that built the modern world. Everything built with concrete in the 20th century, the highways, the bridges, the skyscrapers, the dams, the airport runways, the seawalls, the foundations of every significant structure in the industrialized world, was built with Portland cement concrete. Not Roman concrete, Portland cement concrete. The distinction matters because Portland cement concrete and Roman concrete are, in their fundamental chemistry and their long-term behavior, significantly different materials. Portland cement concrete is strong in compression. It is workable, predictable, and can be manufactured anywhere limestone and clay are available, which is nearly everywhere. It sets quickly, gains most of its design strength within 28 days, and can be produced in consistent, reliable batches. It also, over decades and centuries, tends to crack. The cracking happens because Portland cement concrete is not chemically stable in the long term. The calcium silicate hydrate that constitutes its binding matrix degrades slowly under exposure to water, salt, and temperature cycling. Cracks propagate, water enters. If steel reinforcement is present, and in modern construction it almost always is, The steel corrodes, expands, and accelerates the cracking. The designers of modern concrete structures do not expect them to last 2,000 years. They design for 50 to 100 years. The Roman harbor walls at Caesarea Maritima are still hardening. The Roman Pantheon dome has not been repaired in 19 centuries. The reinforced concrete bridges of the mid-20th century are already showing structural distress. The Romans built better concrete than we do, and we have only recently understood why. The 2017 paper by Marie Jackson's team was not the first study of Roman concrete. It was the first to identify the specific mineralogical mechanism, aluminous tobermorite crystallization, that explains Roman concrete's long-term strength gain. The implications are not merely historical. If Roman concrete gains strength through a reaction between pozzolanic ash, lime, and seawater that produces self-reinforcing mineral crystals, then replicating that reaction in modern concrete design could produce maritime infrastructure, seawalls, harbor structures, offshore foundations, that does not require the expensive maintenance cycles that Portland cement concrete demands. The volcanic ash deposits that produced Roman concrete are still there. The Campi Flegrei fields outside Naples still contain pozzolanic ash chemically similar to what Roman engineers quarried 2,000 years ago. The formula was lost for 1,000 years. It has been found again. Whether the construction industry will adopt it is a question not of chemistry but of economics, of whether the long-term performance advantages of pozzolanic concrete justify the short-term costs of changing supply chains, manufacturing processes, and engineering standards built around Portland cement over 2 centuries. It is the same question that always arises when a better answer arrives to challenge the incumbent one. The incumbent answer has infrastructure. It has investment. It has the inertia of 100 years of engineering education and commercial practice. The better answer has the Pantheon. The Pantheon stands in Rome, as it has stood for 1,900 years, under a dome of concrete that no modern engineer fully understood until 7 years ago. Tourists walk through it every day. They look up at the oculus, the circular opening in the dome's apex, 8.9 meters in diameter, open to the sky, through which rain falls directly onto the sloping floor that drains it away, and they experience what every visitor since 126 AD has experienced. The specific, vertiginous feeling of being inside a space that should not, by any reasonable assessment of what a building can do, still exist. The concrete above them has been setting since Hadrian's engineers poured it. It is stronger today than it was when they were born. It will be stronger still when their grandchildren stand beneath it. The formula was lost for 1,000 years. It is not complicated. Volcanic ash, seawater, lime, time. The Romans did not know the chemistry. They knew what worked, and they built it to last long enough for someone, 19 centuries later, to finally understand why.